Welcome. In this video we will study some rigid motions on the hyperbolic plane. Recall that rigid motions are motions which preserve distances. So this is a function. So rigid motion on a hyperbolic plane would be a function from the hyperbolic plane to itself, such that given any 2 points on the hyperbolic plane, the hyperbolic distance between these 2 points is preserved. So we're going to today discuss a few of transformations of the hyperbolic plane that actually are rigid motions. So the first one, and perhaps the simplest one, is a translation parallel to the x-axis. So crucial for all this will be the remembering the formula for the length of a curve on the hyperbolic plane, which is given by this formula. Right, where this curve is a curve from AB to H, and is given by 2 coordinates, x of t and y of t. And remember, for us curves are always smooth, so these derivatives do make sense. Okay, so this one is particularly easy. So suppose I take, so here's a hyperbolic plane, and I take 2 points and I will do a translation parallel to the x-axis. So that means, in other words, I'm just sort of adding a vector to both of these that has its y coordinate equal to 0. So such a translation arises from or is a shift by a vector of the form x 0, 0. So that means I am not changing anything in the y direction. So let's just look at the formula for the length of a curve. So of course I just want to know that the distance between these 2 points is preserved. But what is a distance between 2 points on the hyperbolic plane? That's the length of a geodesic between these 2 points. So that's the length of a certain curve. So I would like to know that the lengths of geodesic curves are preserved. But in fact, I'm just going to show that by showing that length of any curve between these 2 points is preserved when I do a translation by a vector that's parallel to the x-axis. Why is that? So let's just suppose that we have a curve C between these 2 points, and now I'm not even going to give any equation for it. Let's just quickly look at the formula. So the formula is dx over dt, but what are we doing with the x coordinate of the curve C when we're translating these two parallel? So this is the translated curve. I wonder if I can just draw it the same way. Oh, kind of, okay. Right, so I'm sort of adding here the vector x0, y0, so this distance here is, so if this one was x1, y1, then this one is x1 plus x0, y1. And similarly with these, if this one was x2 plus y2, then that point is x2 plus x0, comma y2. And in fact, any point on the curve whose coordinates were x, y now becomes x plus x0, y. Okay, so let's look at the random point on the curve. This point is mapped to that point under this translation. So the new x is x plus x0, but x0 is a constant, so when I take the derivative, dx over dt, nothing changes. It's still the same derivative as I had with these coordinates. What about dy over dt? Well, y is just the same on the nose in both of them, so dy over dt is going to be the same. And then I have y in the denominator, so that's again the same. So it's clear that just nothing changes in this formula when I do this translation, right? So note. The formula for L of C stays the same when we replace x by x plus 0, x plus x0, and leave y unchanged. You sort of see from here that a translation in the vertical direction, or for that matter in any other direction, would not be a rigid motion, or at least not clearly a rigid motion, because that would change the y. That would change the y. Yes, if I went from, if I added a vector 0, comma y0, nothing would change in the numerator, but that would switch to y plus y0. So the integral gave me a different answer. Okay, but if I'm just interested in shifting things parallel to the x-axis, then that's a rigid motion. What's another rigid motion? Reflection. But again, not just any odd reflection. So 2, a reflection rho m with respect to a line m perpendicular to the x-axis. Is a rigid motion. Okay, so that means if I, so here's as a hyperbolic plane. So if I draw a line M, whose equation, let's say, will be x equal to c, so this is c, then the reflection with respect to this line is a rigid motion. So let's see what happens to a point when I do that, when I carry out that reflection. So if I have a point, let's say x1, y1, and I reflect it, so then what do I get? Well, if this point would have coordinates x2, then m, or c rather, would be the arithmetic mean between x1 and x2. So x2 should be 2c minus x1, and y1 doesn't change. Yeah, let's try that. So if I do this plus that, that gives me 2c. Divide by 2, I get c. So indeed, I get the arithmetic mean between this point and that point to be c. So this is, so if this is point A, then this is rho m of A. Okay, and now let's see what would happen when I substitute this into the formula. See, the y coordinates do not change. So again, nothing changes here and nothing changes there. But, so if this, if I set x prime to be 2c minus x, then dx prime over dt becomes minus dx over dt. Oh, but then I'm squaring these things in the formula. So again, I get the exact same derivative. So again, nothing happens here in this formula. The formula stays the same. So the formula for L of C stays the same if we replace x by 2c minus x and leave y unchanged. So translation parallel to the x-axis and a reflection with respect to a line perpendicular to the x-axis are examples of rigid motions that are rigid motions in both cases, namely on the hyperbolic plane and on the Euclidean plane. Remember that any translation on the Euclidean plane was a rigid motion, and any reflection on the Euclidean plane was a rigid motion, but translation that is also parallel to the x-axis and perpendicular, and reflection with a line perpendicular to the x-axis, represent rigid motions on this planar representation of the hyperbolic plane. However, it is important to remember that this is only a planar representation of the hyperbolic plane. So there might be other rigid motions on the hyperbolic plane that do not distort distances. Remember, a rigid motion cannot distort distances. So there could be other transformations that are rigid motions on the hyperbolic plane that do not look like rigid motions on this planar representation, because they preserve distances in the real hyperbolic world. And on this planar representation, which distorts distances, it might look like this transformation distorts distances, even though it preserves them in reality. And let's look at such an example, and maybe it will surprise you. But an example of such a transformation, which is a rigid motion on the hyperbolic plane, but is not a rigid motion on this planar representation of the hyperbolic plane, is an inversion, and a particular type of inversion. So 3, the inversion, or let's just say an inversion, with respect to a circle centered at centered somewhere on the x-axis, centered at any point of the x-axis, is a rigid motion. On H. Now, we know inversions are not rigid motions on the Euclidean plane. However, this is very nice. An inversion with respect to such a circle on this planar representation of the hyperbolic plane is a real rigid motion in the hyperbolic world. And I was trying to hint at this in the previous video, in the following example. So if we take some point here, let's say its coordinates would be x1, 0, and then we take 2 other points, and let's say their coordinates would be x1, y1, and x2, y2. And we'll look at the hyperbolic midpoint of this line segment. So x1, y0, the hyperbolic midpoint. So let's call this A and this B. So hyperbolic midpoint of the line segment AB. Then, if I draw a circle centered at x1, 0, going through this point, this is the center. So C, circle, centered at x1, 0, of radius y0, then we showed last time that the inversion with respect to that circle, so the center is x1, 0, and the radius is y0 of A was B. So let's just see that this actually proves a bit of that theorem already. Because if I just prolong this line all the way to here, I know that if I'm looking at inversion with respect to this C, then because A is sent to B, therefore B will be sent to A under the inversion. And so every point in between, every point on this line, on this ray, must be sent to a point on this ray. And just by looking at distances, right, everything that is further away from A is going to be sent to something closer away to this point than the image of A, and the image of A is B. So the points that are close to A are going to be mapped to the points that are close to B, and so on. If you keep moving up this line segment, you're eventually going to get to this point, which is sent to itself, and then the points above here are sent back to here. So in other words, this line segment is sent to itself, but of course it's reversed. So the length of this line segment before was just natural log of y2 divided by y1, but after you've applied inversion, you get the same line segment. So the length of it is still natural log of y2 divided by y1. So we already know that inversions preserve the length of these points. These are the distances between these 2 points. So the length of line segments that are perpendicular to the y-axis. So such inversion preserves lengths of line segments. On the line through x1, 0, perpendicular to the x-axis. Okay, but let's have a look at what happens to other geodesics. So again, here's the hyperbolic plane. And suppose I look at 2 points, A and B. And I look at the curve that connects them. So what I'm going to do is I'm going to take a circle centered somewhere at some point on the x-axis. So the center of this point, let's just call this point C, will be here. And suppose that its coordinates is capital C and its coordinates will be little c, comma 0. And I take, and suppose that I take the circle will be of some radius. So some radius k. So this point would be c plus k, comma 0. And this point will be c minus k, comma 0. Okay, so we consider the image. Now I already used up the letter C, so instead of I always denote my curves by C, I'm going to denote this one by gamma. So we consider the image of the curve gamma from AB to the hyperbolic plane under the inversion. So we're going to call, okay, under the inversion, I C K. We denote the image. We denote the image of this curve of gamma by gamma prime. So that's a curve from A to B into H. Okay? You could kind of try to see how this gamma prime is going to look like. So, you know, you can just sort of imagine where the points are going to be mapped, right? I'm not trying to make an exact picture here, but the points outside of the circle are going to be mapped inside, the points inside are going to be mapped to outside. Okay, so this is maybe gamma prime. Very, so this should be actually a little earlier here, right? It's where the point A is being mapped to under the inversion, so you connect the point A with the center, and then, so it's going to be somewhere here. Okay, so this is A prime, and this is B prime. Okay, so we're going to introduce a polar coordinate system like before, centered at C. So if I give myself any point on the blue curve, and I connect it here with the point C, then I'm going to call this R prime. That of course depends on the parameter t. And here's going to be an angle. Here's going to be the angle theta prime of t. On the other hand, for the black curve, I'm going to use non-primed coordinates. So if I take a point here, that's going to be, so I shouldn't, it should really be the same on the same ray here. So I'm not going to write that, but for the points on the black curve, I'm going to write gamma of t is r of t theta of t, and so gamma prime of t will be r prime of t. These are not derivatives, these are just other coordinates. And so this is, so it's a polar coordinate system that is defined in the following way, where x is equal to c plus r cosine theta, and y is just r sine theta. Again, similarly for the coordinates on the point for the curve gamma prime, so this is for gamma, and for gamma prime, it's the same coordinate system. So the relationship between x prime and r prime and theta prime is the same. Okay, but let's first make one observation here, namely, actually two observations. So I want a relation between these r prime and r and theta prime and theta. I know that gamma prime of t is the image under the inversion of gamma. So in other words, we have gamma prime of t. By definition, it's I C K of gamma of t. So if I take a point here, and this point has coordinates r theta, then what are the coordinates of the point on the gamma prime? Look, theta is the same. Theta prime is actually the same as theta, because the point lies on the same ray as the point on the curve gamma. So one, we have that theta prime of t is equal to theta of t. And two, what about the coordinate r? Well, this point is the image under the inversion of that point. So I have that r of t times r prime of t is k squared by definition of an inversion. So that means I get that r prime of t is equal k squared over r of Okay, and I'm not really going to need this picture anymore, or any of this, so let's get rid of it. And now if you watch the video about geodesics on the hyperbolic plane, you will see that there we derived the formula for a length of curve in these kinds of polar coordinates that are centered somewhere on the x-axis. And this was the formula. So in coordinates, r and theta, we have the length of gamma is the integral from a to b of the square root. So the formula was dr over dt squared plus r squared d theta over dt squared dt, everything divided out by r sine theta. Okay, this was the formula from which we got this. This was the formula for length of curve, from which we got the formula that gave us the natural log of cosecant beta minus cotangent beta divided by cosecant alpha minus cotangent alpha. Okay, the way we got it was we first transformed this formula for the length of curve in the Cartesian coordinate system into the length of curve in this polar coordinate system that is not exactly centered at the origin like the standard polar coordinate system is, but it's centered somewhere on the x-axis. So I can similarly write the formula for the length of the curve gamma prime. So in coordinates r prime theta prime, we have that the length of gamma prime, well, it's exactly the same thing. It's a, b, except I'm going to use now the primed coordinates. Remember, prime doesn't mean derivatives. I'm writing d over dt for derivatives. Squared plus r prime squared d theta prime over dt squared. Everything divided by r prime sine theta prime dt. So we have these two formulas. The first one's the length of gamma, the second one's the length of image of gamma, and we want to show that they give me exactly the same number.